Okay, so today I thought we'd do a little bit of a geometric style problem. I want to find the maximal range of a projectile that's launched on a ramp. So in other words, we have a projectile that's being launched at some speed v naught, and let's say that launch angle with the horizontal is angle theta, and this is on a ramp that's inclined at angle phi with respect to the horizontal. So you can either think of that as the angle of elevation from the base or the angle of declination from the apex. So our projectile is going to follow this orange path, and the question is, what is the maximum possible range that we can get? In other words, this distance from the launch point to the end point, that diagonal distance r, what's the maximal value if we're fixed in our launch speed? Now, while we could do this purely algebraically, pull out the trajectory equation, etc., we've done that many, many times, I thought it'd be more fun to do this one a little bit geometrically, using properties of the parabola that we've seen previously. So first off, let's note that the distance from this launch point, and maybe I'll call it point O or something for our launch point, to the directrix of this parabola, which will be, say, somewhere up here. So here's my directrix, D, and then the distance from the launch point up to this directrix, dotted line, we've previously identified that distance is related to the initial kinetic energy of the projectile. So let's go ahead and call this point A, and what we've seen earlier is that AO or OA is actually V naught squared over 2G. So that's a previous result. The idea being, well, if you took this angle theta and you launched it straight up, the directrix will tell you basically what is the maximal height. This orange parabola will kind of collapse down to a ray with its vertex at point A, and we already know from kinematics or energy conservation what that maximal height will be. So that's known. At the same time, we could draw another point directly over here. Maybe I'll call this point B, which is directly over the point where it intersects the ramp eventually. Now, that point will have some velocity. Try not to overdraw here, so I'll call that V or something. That'll be tangent to the parabola at that point, and it'll have some speed that we can also determine by conservation of energy. Now, the key here is, if I finish off this rectangle, maybe I'll call this point C and this point D, we can see that by the same sort of argument, BD would have to be V squared over 2G. Again, the distance from the parabola to the directrix is going to be proportional to the kinetic energy, and we'll have a different speed over there. Okay, so now we can do a little bit of geometry and say that this distance CD is related to this distance R and phi. Pretty clearly, CD is going to be R times the sine of this angle phi. We also already know that AO and CB are the same. So if I want to mark those, say, this is a rectangle here, so we should expect those two distances to be the same. And that lets us write down a nifty little relation because we know that BD is the sum of these two. So since BD is CB plus CD, CB is the same as OA, which is V naught squared over 2G. CD, we just found in terms of geometry, is R sine phi. And then on the other side, BD is V squared over 2G. Now, thus far, we haven't really said anything about this being a minimal trajectory or anything like that. So we'll get to that in a sec. But already we can kind of see this nice relationship between V naught and V in terms of R. Now, of course, we also know that we could have gotten this directly from conservation of energy. It's not really that surprising. This extra height difference is, of course, the MGH that would show up there gives us this. But we got it geometrically here instead. Now let's talk about the minimality. Okay, so for the minimality condition, let's actually draw in two circles. The first one will be a circle centered at O, tangent to the directrix at point A. So notice that since OA is a radius of this circle, that's the same as this distance down to this point right here. And then we could also draw, in general, another circle centered at point D that is tangent to this circle at point B. Now, in general, these two circles, and that's a terrible circle. I'll draw just a portion of it, say. Okay. In general, these two circles will overlap in two places. Maybe I'll mark those in orange here. So in general, these two circles could intersect twice. We know from the properties of these circles that dB, say, the radius of the large circle, will match D to whatever that point is where it intersects the ramp. Same thing we already said about this relation of OA to its other radial component here. But I'm trying to find the maximal range. Or said another way, if I'm given a range, the minimum speed. Those are actually the same question, just asked two different ways. And the minimum launch speed is going to relate to shrinking this circle down as much as possible. Circle centered at O. Because remember, the radius of that circle is proportional to V naught squared. Now, I can't shrink it arbitrarily small and still hope to hit this point D, because in that case, I won't have enough energy to actually make it over there. You can launch it at whatever angle you think is going to optimize it. It might not make it all the way to point D. But as I shrink this circle O, and of course, by conservation of energy, we know that the circle at point D will also gradually shrink, the 2 points of intersection will get closer and closer and closer together until they eventually merge. And there will be a single point of tangency. Let me go ahead and make a version of this over on the side that shows that minimal case. Okay, so here is our sort of simplified version of all that's going on over there. And we can see that in this case where we've shrunk down this circle, and of course this circle has to kind of follow because of conservation of energy, eventually the two will intersect at a single location. I have called that location F, kind of for a good reason, because that point is actually the focus of my parabola. So we've proved earlier that if I have a parabola of minimum speed that's spanning some secant or some chord of the parabola, like here, OD is a chord of this parabola, then this parabola has minimum speed precisely when that secant lies, or rather, when that secant contains the focus of the parabola. So this point F, where these two circles meet, must be the focus of the parabola. We can also see that from the definition of the parabola, because this is a parabola, so the distance of any point on the parabola to the focus must equal the distance to the directrix. OF and OA are, of course, equal to each other because it's a parabola. Same thing with DF and DB, those must be equal because it's a parabola. So this point F being the focus emerges naturally. But now we can see exactly what's going on in terms of the distance R here. Because now R is also equal to OF plus FD. It's this total length of the chord. Okay, but we already have expressions for these based on the congruences shown in the diagram. We know that OF is the same as OA, which again, we've written down, V naught squared over 2G. We know that FD is the same as DB, which again, we've written down here. I could write it in terms of the V squared, but I'd actually rather write it in terms of V naught and stuff, because that'll help us cancel stuff out. And I see that I get a very nice equation that'll let me solve for R directly. So let's see, if we subtract the R over, combine those two equal terms together, and then divide, we should get that the R, and maybe I'll call it R star, to remind us, this R is the maximal distance or range corresponding to a given V naught, or inverted the other way, this V naught will be the minimal V that gets me to this point D. And it will be V naught squared over G, 1 over 1 minus sine phi. Okay, so we have this nice geometric definition or geometric derivation of the maximal range on a ramp in terms of the launch speed. Of course, I could turn this around and solve for the launch speed in terms of a range in case I want to find the minimum speed to reach a particular distance. Now let's see if we can go find what the angle corresponding to this is. Okay, so I've kind of recreated our diagram a bit here. Now I want to find what is the angle that corresponds to this maximal range. So there are a couple ways to do this, but I think that one that's kind of nice that uses a previous result is to use our result from the tangent-secant property of parabolas. So for example, if I look at OD as a secant or as a chord, and I notice that at these 2 points, O and D, there are tangents. In fact, the tangents are constructed from these, from these 2 velocity vectors at those 2 points. I'm doing this very roughly by hand. And those will intersect up at some point here. Maybe I'll call that point X. Okay, so now what we're going to use is the fact that if this chord of this parabola passes through the focus, then the tangent lines that are drawn on opposite ends of that chord will actually intersect on the directrix. My diagram's not great here. It really should have intersected directly there. And actually, they intersect at right angles. So I believe we've proved this before, or if not, we can in an upcoming video. But this is called the orthoptic property of the parabola. Whenever 2 tangents intersect at right angles, that intersection has to lie on the directrix. So that's kind of interesting. And it also lets us sort of chase these angles around to find how this theta is related to this phi in the case of this being the optimal launch angle. Remember, we don't really need to use this formula for R. It's just the fact that OD, being that distance R star, passes through the focus that gives us the information we need here. Okay, so I didn't draw this very well. That really should be a right angle. But let's see if we can now chase this around and see how theta and phi are related. I'll start by defining another angle here. Maybe I'll call it alpha, which is just this angle between the tangent at point D and the ramp itself. And then we can see a couple things. We can see that theta plus phi, that's this whole angle here, plus alpha has to be 90 degrees because of this right triangle OXD. My second relation is going to come from the tangent-secant property that we proved earlier that says that the slope of these 2 tangents at the ends of this chord have to average to the slope of the chord itself. So in our case, that's going to tell us that, so I'll average here, the initial slope is tan theta. Notice that's positive. The final slope is negative, and we have an alpha plus phi with the horizontal. But notice I have to put in the minus sign because alpha and phi are assumed to be positive angles here. And then that should equal the slope of the secant, which is negative tan phi. Okay, so let's take this expression that has an alpha in it and plug it in down here. In fact, I'm just going to replace the alpha plus phi itself with pi over 2 minus theta. Okay, that's not so bad. Now this difference of tangents can be simplified using the tangent difference formula. Let's recall just over to the side how that might work. You might recall that if I have something like tangent of x minus y, this is the tangent of x minus the tangent of y over 1, and then I'm going to make a plus sign, tan x times tan y. In our case, I'm really interested in this difference itself. So I'll multiply this denominator over and I'll get something involving the tangent of the difference. Well, if I do that, what do I get? I will have a tangent of this minus this. Well, notice that's going to be theta minus theta is going to be 2 theta minus pi over 2, all times 1 plus tan theta times tangent of pi over 2 minus theta. But tangent of pi over 2 minus theta is cotan theta. So that's actually going to turn out kind of nice. Tan times cotangent is, well, that's 1. And then 1 plus 1 is 2. So I can see immediately that this term and this 2 will cancel. Okay, now we're almost done. Let's go ahead and use the odd property of tangent. It's an odd function to basically flip this argument here and then cancel the negative sign on the other side. So we'll have tangent of pi over 2 minus 2 theta must equal tangent of phi. And now I can take the arctangent of both sides, and I'll get that pi over 2 minus 2 theta equals phi, or solving for theta, we see that it's going to be 1/2 of pi over 2 minus phi. In other words, if I look at pi over 2 minus phi, that's the complement of this angle phi. That's sort of like this angle, if you want. And we want to let our theta be half of that angle. Another way of saying this is that this angle theta actually bisects the angle between this line that's parallel to the line of axis of symmetry and the line through the focus. This is actually known as the reflection property of a parabola, so we probably could have just jumped straight to that, but I hadn't proved that earlier, so I'll leave that as something you can look up. But yeah, if we think about this line, which is parallel to the axis of symmetry, and we think about this ray or line that's passing through the focus, my parabola tangent line should bisect this angle AOF. Now that angle AOF is 90 plus phi. So if I bisect that, then let's see, this angle up here would be half of 90 plus phi, and then theta itself would be the complement to that, and that's where we get the half of 90 minus phi. Okay, so this is the angle, maybe I'll put a star, that maximizes this range. It corresponds to this distance along the ramp. And all of this was done geometrically without needing to resort to any trajectory equations. QED.